talking about some modular properties of superstring scattering amplitudes.
Thank you very much for the invitation to speak here. I suspect my talk, the subject of my talk is slightly different from the mainstream of talks at this meeting, so I will try and focus on aspects which at least may have a little bit of relevance to the subject of amplitudes in field theory. What I'm going to be talking about will be a very narrowly focused aspect of the structure of amplitudes in string theory, in fact in closed superstring theory. And I'll be talking about the coefficients that arise when you do a low energy expansion in powers of the Mandelstam invariants for these amplitudes. In this talk, I'm going to talk almost entirely about some features of string perturbation theory, which are, in some sense, rather elementary features, but in other senses seem to be very rich in mathematical structure. In particular, I'm going to talk about the coefficients in the expansion of low-order terms in the string perturbation theory, and these coefficients are, in some sense, the theory generates, it's a factory for generating multiple zeta values at tree level and elliptic generalizations of multiple zeta values in one loop, and so on. And that's what I'm going to be talking about for the most part in this talk. So the kinds of functions I'm talking about are the kinds of functions which arise in some apparently rather different, very different looking context in the dimensional regularization of field theories in the way that's been discussed at this meeting. For me, this is just part of a much bigger program, which I'm not going to have time to talk about. I should say that the work I'm talking about here is published in a number of recent papers, mostly in collaboration with Pierre Van Hove and Eric Doka. The larger context, which I'm not going to have much time to talk about, but I'll mention it, is that these perturbative features of the scattering amplitudes are in some sense boundary data. We're trying to understand something much bigger, which is the exact non-perturbative structure of certain aspects of string scattering amplitudes. And that, to the extent that one can understand anything, of course, that's much more ambitious, but whatever one understands non-perturbatively obviously should correctly describe the perturbative approximation. So, I'm going to be talking about the low energy expansion of the effective action of string theory. So let me very quickly just remind you, string theory at lowest order reproduces the Einstein theory of gravity, or supergravity, which can be summarized by the Einstein-Hilbert action, characteristically with this dilaton term, the scalar field theory, the scalar field term. That's the lowest order term, and I'm skipping the fermionic and other fields in the theory. There's a coupling constant. E to minus phi is 1 over the string coupling constant, and there is a dimensional power from the string length outside it. And then there's, of course, an infinite series of higher order terms. So for the theories I'm talking about, the next term in the expansion is of order r to the 4th, which is 3 powers of alpha prime higher than, because it's got 3 extra powers of the curvature. And the curvature is second order in momenta, or second order in derivatives. So this is an expansion in powers of the curvature times alpha prime, or covariant derivative squared times alpha prime. Now, the coefficients here are functions of the moduli, which means effectively the coupling constants in the theory. And so one can imagine doing a low energy expansion and at any order in the expansion, expanding in a power series in the coupling constants. So for the simplest theory I'm going to talk about, there's one coupling constant, E minus phi, and one can imagine taking any term in this expansion and expanding it in perturbation theory, which is what I'm going to be talking about. These moduli, of course, they were first seen in the supergravity theories that were constructed in the 1970s. In particular, the moduli for the theory I'm talking about, which has its ancestry in 10 dimensions, in type 2 theories in 10 dimensions, when compactified on a torus down to lower dimensions, one gets an increasing number of moduli. There is invariance under the duality group G, and the moduli parameterize a coset space of G over K, where K is a maximal compact subgroup of G. And this sequence was first written down, it was very famous, by Clement and Julien in the 70s. Now in string theory, unlike supergravity, this continuous symmetry group is broken because one has to make discrete identifications of the moduli, so that only an arithmetic subgroup, G of Z, G of Z, is preserved in string theory. In supergravity, in perturbation theory, the continuous group is preserved, but this breaking in string theory occurs even at tree level. So there's only the duality group is a discrete group, even in tree level. This is the duality group for the whole, the S-duality group, if you like, the non-perturbative duality group. If one's doing perturbation theory, then one's expanding around a boundary of moduli space, and in particular, if I expand in powers of G, e to the phi, then one gets the usual picture of an expansion in terms of Riemann expansion in powers of G multiplying Riemann surfaces with higher and higher genus. So the tree level is a sphere, one loop is a torus, and so on. And associated with the integrand, one has to integrate over the Riemann surfaces, and one has to integrate over the moduli of those surfaces, and in particular, the one loop amplitude, which I'm going to talk about at length, is associated with a complex structure which transforms an SL2, and for the higher loop cases, you get higher worldsheet automorphic symmetries. But I'll be talking largely about the SL2, so let me just remind you that SL2 means that the complex structure tau transforms in the standard way, non-linearly, it's A tau plus B over C tau plus D, where A, B, C, and D are integers, determinant 1. So that's one aspect of the modular symmetry that occurs in the title of my talk. Another aspect, which I'll have very little time to talk about, is the fact that so this modular symmetry is to do with the worldsheet torus. Another SL2 occurs in the simplest example of the S-duality groups. Simplest example being the SL2 of the type 2B theory, where the target space complex structure is transformed. So let me now go to talk, most of the talk is about 4-graviton scattering, most of the explicit formulas. Let me just remind you, 4-graviton scattering in the maximally supersymmetric theory has this extremely simplifying feature that you can factor out front a power of r to the 4th, where this r is the linearized curvature, so it's 2 powers of momentum times the polarization tensor, and that multiplies a scalar function of the Mandelstam invariance and of the moduli, and in the simplest 10-dimensional type 2B theory, there is one complex modulus, omega, ST and U of Mandelstam invariance. And then by Bose symmetry, basically, T is a symmetric function of ST and U, which are subject to the constraint S plus T plus U equals 0. And then you can easily see that T has a power series, if the analytic part of T has a power series expansion in powers of what I've called sigma 2 and sigma 3. Of course, the non-analytic pieces are absolutely central in discussing the amplitude, but they're not important for this talk, so I'm not going to mention them. So that the analytic part of T can be expanded in a power series in sigma 2 and sigma 3. And so it's indexed by two integers, P and Q, and it's got coefficients which are functions of omega, the modulus, and more generally, when one talks about the higher rank duality groups that you get by coming down on a torus, there will be many moduli, but in the simplest case, the modulus, the simplest non-trivial case being the type 2B theory, the coefficients are invariant under the S-duality group, which is SL2 in that simple case. So this is the other SL2 that I mentioned, and that's the other modular aspect in the title of my talk, but I won't be saying very much about this one. So in order to understand the S-duality invariance of the amplitude, one really has to know something about these coefficients. And the major part of the program, which is not the subject of this talk, would be the extent to which we can determine these coefficients exactly. But in the absence of determining them exactly, one can try and ask, what about the perturbative expansion? The boundary data is the perturbation expansion around the boundary of modular space, the small coupling expansion. So let me talk about that. So here we have the amplitude that I wrote before. This is the same constraint. So I'm going to talk about these perturbative contributions to the amplitude, starting with reminding you about the tree-level expansion. So this tree-level amplitude, the 4-point function, is very well known. It's been around for many, many years. And in this case, the amplitude defined by a functional integral over a sphere with 4 vertex operators is simply contained in this scalar function E0, which is a very well-known ratio of the product of Demner functions, dating back more or less to Villazoro's model of the late 1960s in the bosonic case, and this is the supersymmetric version. So this has an expansion in powers of S, T, and U, and multiplying R to the 4th, any power of S, T, or U corresponds to, in the language of effective action, corresponds to some derivative of the R to the 4th. So you can translate this expansion into terms in the effective action in the way I'm about to describe. And using elementary properties of gamma functions, here I've just written out the first few terms, which is enough to illustrate what I want to illustrate. Sigma 2 and sigma 3, let me remind you, are these objects. And then these terms, which are higher and higher orders in alpha prime, or higher and higher powers of S, T, and U, correspond to terms in the effective action of this type. So these are higher and higher derivative terms on R to the 4th. The first term being the supergravity term. 1 over sigma 3 is the same as 1. So 3 over sigma 3 is the same as 1 over STU. And so supergravity packages into this first term. And then there are, of course, an infinite number of subsequent terms. The characteristic feature, though, is that these terms have coefficients which are rational numbers times powers of zeta values. And these are odd zeta values. So that is the feature which is important to take away from this. This is the very simplest example where you see that there are zeta values coming in which are, of course, interesting for us here, but they're also interesting in the context of renormalized quantum field theory. Now, how does this generalize to the n particle case? Let me first give you a very, very brief summary. I should say this talk is also being prepared for people who don't know anything about the subject. So I'm going to give a very brief summary of things that you almost certainly already know about zeta values and multiple zeta values. So I will fly through this transparency. Zeta values can be thought of as special values of polylogs. Evaluated as A equals 1. Even zeta values are simply some coefficients times powers of pi. Odd zeta values are presumably transcendental numbers, but nobody has ever proved that any of them are transcendental. And they're presumably independent of each other, therefore. Multiple zeta values are special values of multiple polylogs, which are defined in this way. And the special values mean you evaluate the multiple polylog when the arguments are equal to 1. And that gives you the standard formula for multiple zeta values. The multiple zeta values have a depth, which is the number of arguments, R, and they have a weight, which is the sum of the arguments. I'm saying all this even though it's very familiar, because I'm going to come into analogous context, which is less familiar later. You could ask, why are multiple zeta values interesting? And I must say, I have asked mathematicians why they're interesting, and the argument, there's nice arguments, but very often it's a sort of circular argument. They're interesting because they occur in Feynman diagrams. Or they're interesting because they occur in string theory. But as far as I can work out, I think one of their interests, of course, is that they are numbers, but they're numbers that satisfy algebraic properties. And it's these algebraic properties which, of course, have been the center of a huge amount of work in mathematics and also in this kind of area of theoretical physics. The first case in which a multiple zeta value cannot be reduced to a sum of polynomial in ordinary zeta values is a weight 8. So zeta 5, 3 cannot be written in terms of ordinary zeta values. And I've just made the comment, of course, that as far as this conference is concerned, they arise in a big way in the analysis of Feynman diagrams. Now, there's been some beautiful work in a large number of papers, starting with papers by Stieberger, and then Stieberger and his collaborators, on expanding the tree-level amplitudes that I mentioned before, but now for the endpoint function, when n is bigger than 4. And there you get this a very beautiful structure arising. It's, in a sense, these string amplitudes are generating functions for multiple zeta values, where they arise with great in profusion. So for open strings, the expansion of tree levels gives you coefficients which are multiple zeta values with weights which are correlated with the power in the expansion. And for closed strings, again with n bigger than 4, the coefficients are single valued multiple zeta values, which were discussed somewhat yesterday and will surely arise again because these things now arise in this different context of dimensionally regularized quantum field theory. They were discussed in the mathematical context by Brown and also by Stockholm, Stieberger, and maybe others in the context of the expansion of closed string amplitudes. So these single value multiple zetas are they're called single valued. You might ask, how can a number be single valued? Well, the number is single valued. The word single valued in front of multiple zeta is the statement that they can again be thought of as special values of multiple polygons, but in this case they're single valued multiple polygons. Multiple polygon has a dependence on a complex variable, and the single valuedness means there's no monodromy. And they're generalizations, if you like, of the Boch-Wigner dialogue. So these single-valued zeta values, the single valuedness kills the even ones. So the even zeta values disappear when you ask them to be single-valued. And the odd ones are simply the same, well, up to a factor of 2, the same as the ordinary odd zeta values. In this case, the first non-trivial example is a weight 11, where the single-valued multiple zeta value at weight 11 could be written in terms of ordinary multiple zeta values in this way. So the question for this talk is, that was all introductory, the question for this talk is, how does this generalize, in what context does this generalize to a higher genus? Well, needless to say, it generalizes in the context of string theory when you try and do the same expansion, the low energy expansion, but now not of tree level, but of the one loop amplitude. So although the tree level expansion was almost trivial, given properties of the ratio gamma functions, it is far more difficult to do the genus 1 expansion. Sorry, when I say it's trivial, I meant for the 4-point function. It's very non-trivial at tree level for the n-point function. So here I'm going to go back to the 4-point function. 4-point function at one loop is given by an integral over the complex structure tau. Tau I've written as x plus iy here. So it's an integral over tau, say d2 tau, over the imaginary part of tau squared. So this is the SL2 invariant measure times a modular function b, where that modular function is itself given by the vertex operator construction. It's given by taking the expectation value of 4 vertex operators on this torus at fixed tau, And that expectation value involves the exponential of the Green's function between any pair of points with ki.kj multiplying that Green's function. So what you have to do is integrate over the 4 points and then integrate over the complex structure. But already, before you integrate over the complex structure, you've got this very interesting looking modular function. And it's these modular functions that I'm going to be talking about mostly. So this is a kind of modular function which we in string theory are very used to looking at, but which mathematicians are not used to looking at least as far as I can tell from the ones I've spoken to. They are quite fascinated by the fact that this is not something which they have looked at in great detail. So if I want to expand this in powers of ST or U, the alpha prime expansion, I have to bring down powers of the Green's function. The low energy expansion then involves bringing down powers of the Green's function and then integrating over the positions of the vertex operators. In a number of different papers, we've looked at this, and well, I'll tell you what happens. The subject is by no means complete. So the general statement is that you bring down W powers of the Green's function, and then you have to evaluate this integral, and what this integral is, the powers of S that come in, this will again be rewritten as a power of sigma 2 times a power of sigma 3 times some coefficient function tau, j of tau, summed over all possible ways in which, for a given weight, you can get powers of sigma 2 and sigma 3. So these j's contain, the j's are modular functions which contain a sum of terms involving Green's functions. So what we're really calculating are simply very trivial looking Feynman diagrams on a torus. The Feynman diagrams are given by taking the powers of Green's function between pairs of points. And then the coefficients, in the end, if you wanted to get the actual coefficient obtained by integrating over tau, you'd integrate these j's over tau. So the question is, what is the structure of these Feynman diagrams? Each Feynman diagram, each j is a sum of Feynman diagrams, where each Feynman diagram is invariant under SL2. The whole function is modular invariant, but each Feynman diagram is modular invariant as well. And it's constructed from propagators which are formed from Green's functions on the torus. So this is the standard Green's function on a torus in terms of the Jacobi theta function, theta 1. This is a doubly periodic function in the 2 periods of the torus, so you can do a double Fourier expansion with integers m and n, coefficients. So if you go to a basis where z is written as u plus tau v, this is a natural thing to do on a torus, then this is a double periodic function with a constant term, but the constant term drops out when you evaluate the amplitude because this multiplies s plus t plus u. So we can drop the zero mode, and the m and n are then non-zero integers, which are the integers satisfying this condition, which are the discrete momenta on the torus. So if you go to momentum space with the propagator, where this g hat is simply, this is the propagator on the torus. So nothing could be simpler. This is a bosonic propagator on a torus, and all I'm doing is joining points on that torus in all possible ways. So I could draw a diagram for the 4-point function where I have lines joining pairs of points, where you represent where the vertices were, and then I've put a number of lines, L1, L2, L3, L4, L5, L6, which are the 6 possible ways kinds of propagators you get. And this is the general diagram for the 4-point function. So it's a power of, just powers of the Green's function joining pairs of points. The thing that is tricky, the thing that is unfamiliar perhaps compared to conventional Feynman diagrams, is that these are momentum sums. Each loop here involves a momentum sum. There's momentum conservation at each vertex. The Feynman rules are the usual Feynman rules, with sums instead of integers, instead of integer sums instead of intervals. And everything's finite. And the answer is a finite sum. Finite number. So the weight of the diagram is simply the number of propagators, and it will contribute a term to, weight W will contribute to e to the power 2W r to the fourth. So let me just give a few examples. The very simplest example is a function we'll call d2, which is simply two propagators joining a pair of points. One propagator vanishes because because I have no zero mode, when I integrate I get zero. So two propagators joining 2 points. It simply gives me the square of the propagator, and that's a well-known function. This is the Eisenstein series, the non-holomorphic Eisenstein series, E2, where in general the Eisenstein series is defined this way. So what the diagrams I'm about to show you are generalizations of Eisenstein series. Eisenstein series, of course, have been the subject of a lot of interest in various ways in mathematics. These functions are generalizations of Eisenstein series, which also have fascinating properties. So, for example, there's an infinite sequence of terms, which I'll just show diagrammatically, involve lines with joining 2 points. But here we've got one line joining 2 points, here we've got a pair of propagators, and one propagator, and so on. So you can have any number of propagators, A, B, or C, joining linking two points. And so that's what this symbol CABC means, and they contribute to higher and higher order terms. This particular sequence, I can write the multiple sums. See, these are two-loop diagrams. This is a one-loop diagram, this is a two-loop diagram. This sequence of two-loop diagrams is given by multiple sums which take this form, just the A powers of the propagator, B powers of the propagator, and C powers of the propagator. Very, very simple to write down. Extremely difficult to analyze. We tried very hard to analyze this, but more to the point, Don Zagier tried very hard to analyze this. He analyzed the first non-trivial case, C111. So he managed to calculate that by brute force. But we eventually managed to find a way of understanding this whole sequence by realizing that they satisfy Laplace equations, Laplace eigenvalue equations. The C111 satisfies this equation, and its solution is a very simple solution, which is the one Zagier found. And then there are higher weight terms which satisfy more complicated equations. And in fact, there's an infinite sequence of such Laplace equations. So there's an infinite nested sequence of Laplace equations, and you can understand all of them. You can understand the general solution in terms of Eisenstein series. So these, on the right-hand side, these are the source terms are powers of Eisenstein series. And there's a very fascinating series of equations there. When you go, if you look at the actual diagrams that contribute to the amplitude, however, you go outside of this special set that I'm talking about. This infinite sequence of diagrams doesn't even include all of them. And in fact, you need to include diagrams such as this one, which isn't one of that set, or this one is. This is C211. This is not one of the set. So at this order, you get weight 4 diagrams. At the next order, you get weight 5 diagrams, and this is just a set of diagrams that you have to calculate. Calculating these diagrams is ferociously difficult. In fact, I don't know a systematic way of doing it, but by experimenting, I'll tell you in a minute about some fascinating relations between these diagrams, which allow you to evaluate them. But let me first say that these diagrams, you should think of them as being the elliptic analog of multiple zeta values. These are functions of tau, but they are, in fact, they can be identified as special values of single-valued elliptical multiple polygons. So let me just say a word or two about that. So here's a statement I just made, that one of these diagrams, what we've called modular graph functions, but they are really elliptical multiple zeta values, are single-valued elliptical multiple polygons evaluated at special value of the argument, just as multiple zeta values are special values of multiple polygons. And the way to see that is actually, in fact, incredibly simple. You take one of these diagrams I just mentioned, which is the integral over 4 z's. This is a particular one with one propagator joining each point, pair of points. And now break apart one of these points. Don't integrate over z1. And just break it apart and introduce an extra point like this. Then it's very easy to see that this diagram, which is a function of zeta, zeta being the difference, the exponential of the difference between z5 and z1, this diagram is a function of zeta, but it's a single-valued function of zeta. And you can see from its structure that it's a single-valued elliptical function of zeta, and you can write it down, you can expand it in terms of elliptical polygons. And then it's very easy to see that if you set zeta equals 1, or z5 equals z1, it reduces to one of these functions. So here's the statement that this is a single-valued elliptical multiple polygon, this diagram here, and it reduces to these modular graph, this modular graph function when you take its argument to 1. And another statement is the way we discussed this was by generalizing in 1990, Zagier in fact introduced the notion of a single-valued elliptical polygon. And these Ds that we've got here are generalizations to multiple polygons of his single-valued elliptical polygon. So some statements, some general statements. First of all, I made that this is the statement on the treeless transparency. The real heart of what I'd like to talk about, but first I haven't got time, secondly you wouldn't have the patience to listen to it because it's so complicated. But the summary of what I would like to say about these properties is that there are pretty amazing looking identities between these functions. These are functions of tau. So here, for example, this is just one of these identities. At weight 5, those identity relates to the function I call d5. I won't bother to draw these functions for you, but these are weight 5 functions of the type which I had earlier. But this is a 4-loop Feynman diagram. This is a 3-loop Feynman diagram. This is a 3-loop Feynman diagram again. This is a 1-loop Feynman diagram. So this is the relation between weight 5 functions with different numbers of loops. And you should bear in mind the corresponding statements about multiple zeta values, where you have polynomial relations between multiple zeta values of the same weight, but different numbers of different depths. So the number of loops is really the depth. And so this is a polynomial relationship between weight 5 modular graph functions. And here's another one with weight 6, and we've got a number of these things. Proving these things turns out to be exceedingly difficult. At least we don't know how to. We have not found an efficient way of proving them. But we have to brute force the sum. These are multiple sums, and there are tricks for doing multiple sums. What we found, the cleanest statement I could make is there's an experimental fact that for any such polynomial that vanishes, you see that you guess the polynomial might vanish by looking at its asymptotic behavior near the cusp, near tau 2 goes to infinity, and you discover that the power series in tau 2 vanishes. That's the Laurent series. The vanishing of the Laurent series, which is incredibly subtle because the Laurent series contains multiple zeta values, so the fact that this particular combination, well, when you get to actually have to go to a higher order of this, when you get to high enough order, the statement that the Laurent series vanishes is a property that uses the algebra of multiple zeta values. But when it does vanish, we discovered experimentally that applying this Cauchy-Riemann type operator a certain number of times, w minus 1 times, kills the polynomial, and then you can prove the whole polynomial vanishes. So we managed to prove these relations that we have at these low orders, but we haven't got a general proof. The conjecture that follows from that, though, is that this happens generally, that these modular graph functions of any weight satisfy very non-trivial looking polynomial relations with rational coefficients, rather like you may have been used to seeing for multiple polygons, multiple zeta values. And just as in that case, that raises the obvious question, is what is the basis for these functions? because if they satisfy relations, the basis of such functions is much smaller than the number of functions of the given weight. I should say that there is work which is presumably related to this, although as far as I know, the relationship is not yet understood in detail, that arises from thinking about open string loop amplitudes, work in particular by this set of authors, which involves a different kind of elliptical multiple polylog, which is a holomorphic or almost holomorphic function introduced by Brown and Levin a few years ago. But the precise relationship I don't think is understood. It's something, what one hopes for is something like the KLT relation between, at tree level, between the open string and the closed string, that should generalize in some sense. And then another thing I haven't talked about is the fact that these modular functions, in fact, there's an important generalization of them to modular forms, which is a very natural generalization. And then, so let me in the last few minutes just say a bit more. Having found out some properties of these functions, enough properties to evaluate the low order ones, we can go ahead and expand the one loop amplitude, integrate over the fundamental domain, which you need to do to get the coefficients in the amplitude, and then you get coefficients which again are rational numbers times ordinary zeta values up to the order at which we've done it, which is not very high. So these are the coefficients at one loop that look analogous to the ones at tree level. And then the question is, what is the relationship between them? Well, the relationship between one loop and tree level is something non-perturbative, of course. And that has something to do with S-duality, the part of the talk which I'm not going to be able to give. Let me just make a couple of comments about high genus. So genus 2, much less is known. Genus 1 was difficult enough. Genus 2 is really quite difficult. The amplitude was written down 10 years ago by Doker and Fong, and then Doker and Gupta and Fong looked at the lowest order term of the expansion, and more recently, with great difficulty, we managed to get the second term of the expansion. But that's the limit at the moment. That's the term of order d to the sixth or to the fourth. At 3 loops, almost nothing is known except for the heroic work by Gomez and Mafra, who analyzed the 3 loop amplitude at using the pure spinor formalism, and they found the leading low energy behavior was of this form, again a rational number times a zeta value. Beyond that, absolutely nothing is known explicitly. Of course, there's a lot that's known, a huge amount is known in string perturbation theory for arbitrary genus in principle, but in practice, extracting an actual expression is very difficult. Since I have 1 minute left, perhaps, I can just mention that all this was the perturbative background to something which one would hope to understand non-perturbatively, by seeing how strong the constraints of duality and supersymmetry, for example, constrain these coefficients. So, in the 10-dimensional type 2B theory that I've been talking about, where there's one complex structure, one complex modulus, whose imaginary part is the inverse of the string coupling, the duality groups SL2, and you can look at the constraints on at least at the low order in alpha prime constraints, the low powers of P and Q. You can actually understand something by using a combination of supersymmetry and duality. And you can understand that the coefficient, for example, the lowest order coefficient, which is the coefficient r to the 4th, satisfies a Laplace equation in the moduli space with an eigenvalue of 3/4, and the next term, the 4th r to the 4th, has a Laplace equation with eigenvalue of 15/4. This just follows from supersymmetry, actually. And these equations have unique solutions, subject to the power behavior, subject to the fact that we know that the power behaved at weak coupling, the power behaved in the coupling constant. And the solutions are non-holomorphic Eisenstein series, which I've mentioned earlier in the context of the world sheet. expansion. And then you discover that when you expand the solution, you get a tree-level term, for example, after the fourth term, you get a tree-level term and a one-loop term, but no other perturbative terms. You get an infinite set of instantons. The coefficients here correspond precisely to the coefficients of the tree-level and one-loop term that I mentioned earlier. That's the ones, I wrote them in modes before to highlight the fact that they actually correspond precisely to the values that you get from this argument. So this non-perturbative argument is reproducing the perturbation theory coefficients at tree level and one loop. The same is true at the next order for after the e to the fourth after the fourth term. There is a tree level and two loop term. There's no one loop term, which agrees again with perturbation theory and string theory. So the string perturbation theory precisely gives this answer up to two loops, and then an infinite set of instanton contributions. And then I will flip through this because I don't have time, but the next term, e to the sixth after the fourth, gives you a genus 1, genus 0, genus 1, genus 2, genus 3 coefficients, which again exactly agree with what is known in the explicit string theory perturbation expansion. So there's a matching between the constraints of duality and supersymmetry and the explicit calculations from string theory. So my last transparency is simply an empty statement maybe, but a fantasy which is oft repeated, which is string theory contains no ultraviolet divergences to any order, even though we haven't explicitly written down the expressions, apart from the very lowest order expressions. But since we know there are no ultraviolet divergences in string theory, and since we know that the low energy limit of string theory is supergravity, there should be a correspondence between what you see in string theory and what you see in supergravity. And indeed, up to 3 loops, the ultraviolet divergences that you see in supergravity in higher dimensions, there are no divergences in 4 dimensions, but in higher dimensions, there's logarithmic divergences appear in critical dimensions depending on the loop number, and you get logs. These logs are precisely reproduced by the modular properties that I've been talking about in a way which I haven't explained, but that suggests that maybe there's some way of understanding the origin of the ultraviolet divergences that will eventually be discovered in n equals 8 supergravity, for example, in 4 dimensions. I'm looking at the limit that gives you supergravity from string theory. So that it's a question, or fantasy, is to try and understand since all the Feynman diagrams of supergravity are packaged into a single expression in string theory at any given genus, and since this string theory has no divergences, there ought to be a way of taking a limit in which one sees why divergences arise or why they do not arise in the field theory limit. So I'll stop there.
So, have you thought about understanding this relation between the multi-zeta values from the perspective of the worksheet perturbation theory, home perturbation theory?
So
you write down this relation between the multiple zeta values, right? Is it possible to understand these relations from the worksheet conformal field theory?
So you're talking about the ordinary multiple zeta values?
Yeah, the relation.
The ones which come at tree level?
Yeah.
There's some experts in the room who are able to answer that question more than me. I haven't.
Any other question? There in the back.
So once you've derived the Laplace equation for a given function, how much more sort of boundary information do you need to uniquely determine it?
Well, there were 2 kinds of Laplace equations I had. I had ones for the worldsheet Feynman diagrams.
Or I'll ask for both of them then.
Well, in both cases, knowing the behavior near the cusp Well, and you don't need, well, not knowing the behavior, knowing that the behavior near the cusp is, at worst, power behaved in tau 2 or in omega 2 in the case, usually determines the solution.
You don't need to know sort of explicit coefficients in front of that power behavior, you just need to know that it's power behaved, and that's enough to
Yes, yes,
make the Laplace equation.
yeah.
Thanks.
Any other questions?
If you try to look at the bosonic stream, okay, there is divergence because of the tachyon and dilaton, but maybe the same structure for this general function appear also there.
I mean, to a very limited extent, I tried looking at that, but got confused. I do suspect that you're right, that there is some interesting structure there. It's easy to get confused because of the divergences with the tachyon.
But I mean, the multi-loop are known to any order of loop explicitly.
Well, of course, in loop amplitudes, it's yes, yeah. The trouble is it's not well defined because of the divergences.
Any other questions?
You show that you have fixed weight relations which involves coefficients with at different loops, right? If I understood correctly.
The Woj values.
Exactly.
Yeah.
How this adds information for the amplitudes at loop level? What's the aim?
Oh, sorry, at the point which I didn't explain actually, the point where we get those relations enables us to rewrite what is in fact some very complicated function in terms of other functions that we know already, so that we can then, the integration over the bit I skipped was how you integrate over the complex structure to get the final coefficients. So I wrote functions of tau. In the actual perturbation expansion of string theory, you then have to integrate over tau. And that final integral over tau is itself very tricky. But knowing those relations helped us understand how to do that integral. So the spin-off for us is that, but I mean, much more, I mean, from the mathematical point of view, such relations look very fascinating. They are the elliptic generalization of relations, similar relations that occur for multiple zeta values. So, for reasons, as I said earlier, that I don't quite understand, this seems to be quite of some interest to mathematicians.
Any other questions? Not the best thing, my opinion.